Welcome back. Lesson 16, Part A, we're getting there. This is seriously the last major new topic. We've done regression, we've done probability, we've done sampling distributions, we've done confidence intervals, graphing, descriptive statistics, collecting data, and finally, hypothesis testing. There's a ton of big ideas in these lectures here for lesson 16, so make sure you pay attention. We want you to understand the process, so we're going to go slow at first and then with each additional example a little bit quicker, and we'll throw one more layer on the cake. But here we go, lesson 16, running a hypothesis for one proportion, but all of the general hypothesis testing ideas come in this unit, so super important lesson. All right, example. A few years ago, an ABC News poll stated that 44% of all Americans surveyed say that they drove an SUV, minivan, some kind of truck, so we'll just call that a large vehicle. Here at the college, we notice almost everything in the parking lot seems to be something bigger than a car. Well, I noticed it, because I drive my little Scion, and I can't see when I'm backing out of my parking spaces typically, so we'll run a hypothesis test to see if at the college more than 44% of Cecil College drivers prefer large vehicles. This problem, I wrote this problem as sort of a personal problem. Like, I think that more than 44% of all the vehicles are large, but it's just based on anecdotal evidence. It's kind of neat, park it next to these monster trucks and you can't seat it back out. So what we're going to do is we're going to actually run an official hypothesis test. We're going to test my claim. Okay, and so all that being said, here we go. We'll incent some students to roam around the parking lot on various days using good sampling techniques. Here's what happened. They actually got 100 large vehicles and 90 small vehicles. And the data can be summarized as what? Well, think about this here. It's a categorical variable, right? We're still in this p-hat mode for just another chapter or two. Either a car is large or small, so the data can be summarized with a proportion. Comes from a sample, so it's p-hat. And let's see. We care about the large, right? So we'll put 100 on top. How many vehicles total? The sample size was 190, 100 plus 90. Right, down below, so this is 100 over 190. Definitely more than half. What does it turn out to be? 52.6%. 52.6, or as percentage, 52.6%. Now, we'll typically be working everything in proportion form here with decimals as we do the calculations and so on, but maybe at the very end it's easier to think in percentages. All right, now ask yourself this, viewer, are you convinced? Right? We'll never be able to get a handle on it. Look, the vehicles in the parking lot at Cecil College, it's like perpetually changing. I could even take an aerial photograph of the whole parking lot and I still wouldn't know the answer if more than 44% of all drivers are driving large vehicles, right? People are leaving, coming in, some people aren't on campus that day, might own a couple of cars. Here's the data. I have to use the data and either convince myself, does this convince me it's more than 44%, or am I not overwhelmed? Okay, so we're going to use this data to run the hypothesis test. All that stuff when we did sampling distributions 2 lessons ago comes into play. We need to build a temporary working model. Whenever you hear model in this class, basically we've got a couple. One of them is linear, but we've sure been talking about normal models for a while, and this is going to be normal model as well. Bullet point, we need a temporary working model, so what we're going to do is assume at Cecil College 44% of our drivers prefer large vehicles. We need a starting point to cook up the model. Now remember, I think it's more. That's my claim, that's my theory. But ABC News said 44%, so I'm going to just start at 44% here at the college, and I'm going to cook up a model based on that assumption. We're going to cook up a model based on this assumption. The assumption might be correct, might be incorrect. We don't know, but we have to start somewhere. The whole rest of the course, what are we going to run? We're going to run tests. Hypothesis test officially, but a lot of times instructors and people will just say run the test. Right? So we'll test. We will test whether or not, based on our sample, we collected that data on the previous slide, is there compelling evidence that more than 44% of our drivers prefer large vehicles? That 52.6%, is that compelling enough to convince you that overall at the college, more than 44% prefer those large vehicles? When we run these tests, there's two hypotheses. You need to write those down. It's sort of like step one of the whole process. I'm going to write them all out in words for this example. When Kim gets to the official steps in video 2, or video B, I should say, there are symbols to sort of shorthand, but for now, first example, we'll just write it out in words. All right, null hypothesis. Capital H, little subscript 0. This would be called the null hypothesis. You could say H sub 0, you could say H naught. Either's fine, but all right. This is the original assumption up top. So what am I going to say for the null? I'm assuming that 44% of Cecil drivers prefer large vehicles. So H sub 0, 44% of Cecil drivers prefer large vehicles. Let me put in parentheses, it's not part of the hypothesis, but this is assumed true. Assume is sort of a big word, right? But to start this process, this is assumed to be true here at Cecil College. The alternative hypothesis, this is as the runner of the test, as the person doing the test, this is what I think to be true. But we need to collect the data to confirm it or not confirm it. So, alternative will be H sub A, right, for alternative hypothesis. And what do I think? I think, well, whole thing except put two words in front, more than 44%. All right, so here's what I think. I think more than 44%. I'll just say prefer large vehicles. More than 44% prefer large vehicles. If you're being very proper, put Cecil drivers, but wouldn't fit on a line on the screen. All right. When Kim gets to video B, there'll be symbols for all these words and sort of make it a little bit cleaner looking. All right, so we've got our hypotheses, and we understand sort of what they're telling us. Now, students, ask yourself this question. What would convince you? What would convince you that I'm right? My claim is correct. What would convince you that more than 44% of all Cecil drivers prefer? For one, certainly the sample proportion when we collect that data surely has to be bigger than 44%, has to be larger than 44%. Right? The claim is that it's more, greater than. So when I collect my data, say you collect your data and you get p hat equals 0.414, it's basically game over. There's no evidence whatsoever that I'm right. But that didn't happen, all right? So get rid of that. The question you're asking yourself is, how much larger does it need to be? What was our p hat, students? This 52.6%, all right? So our p hat was 0.526. This is certainly larger than 44%. Is it larger enough? Is it enough bigger than the 44 to convince you, right? There's no more eyeballing it. There's no more guessing. We're gonna rely on the model. The temporary working model, the one based on our assumption, Remember what we're assuming. We're saying, all right, to start at Cecil P's 0.44, let's build the model. Okay, we learned 2 lessons ago. P hat follows a normal model under certain conditions. We can get the mean, we can get the standard deviation. Using those facts, then we'll decide is this big or not. It's easy. When we go, you're gonna say, wow, I kind of know how to do this already. Now we're just calling it a hypothesis test. All right. Make sure I'm in the right spot. I am. Top of the next page, bullet point, the standard deviation is the key. How much larger is based on the standard deviation of the sampling model? We calculate it based on this assumption. Remember, we're assuming for Cecil P's 0.44, so when I do the standard deviation estimate, I use that one. I don't use the data. There's a little bit of a difference between confidence intervals and hypothesis tests. And just note that we've got to be careful to get the right numbers. So let me just make sure what I called it here. All right, so let's call this the standard deviation of P hat. SD for standard deviation of P hat. And I'm just gonna, let me see here. We know the form of it, right? We've been working with this P1 minus P thing for a couple chapters. What I want you to do, put a little 0 here, subscript, just to emphasize. Remember, the null hypothesis was H sub 0. Little P sub 0 tells me that pick the number that's listed in the null hypothesis. So we'll put P sub 0, 1 minus P sub 0 over n. The point is that's the number. All right, so we'll get it. Here's 0.44. All right, and then 1 minus 0.44 is 0.56. Dollar minus 44 cents, 56 cents. Sample size was what for this problem? Let's see, 190, right? 190 cars. Vehicles, I guess I should say. Here's the standard deviation. Now, before I give you the answer, I know you can get this, but you're thinking, is the 52.6% very large compared to a 0.44? I'm going to use this as sort of my ruler. I'm going to use this as, is it large, right? So, we crank this in the calculator, we get a 0.036. That's the standard deviation of P hat, under the assumption that the null is true, under the assumption that the null hypothesis is true. When we compare the data to the hypothesized value, it's in terms of this number right here. All right, flip the slide. Next bullet points. Using the assumed model, the one centered at 0.44, with a standard deviation of 0.036, we can ask ourselves, just how unlikely would it be to actually draw our sample proportion of P hat was 0.526? Right? Kind of see, like, how many of these is this away from this? If you know what I mean, right? How many of those standard deviations is the 526 away from the 0.44? All right, so we draw on everything. I love this unit. Everything important we learn the whole semester just comes back, and let's remember z-scores. Typically when running hypothesis tests, the sample proportion gets standardized. It basically means convert to z's. So we'll do that now. Convert the sample proportion to a z-score. Z equals, let's see here, what are we going to do here? Basically, I'm going to take my value I'm concerned about, which turns out to be P hat, right? And I'm going to subtract off the hypothesized value, which I guess we could call P sub 0, and I'm going to divide it by a standard deviation of P hat, right? So that's in symbols if you want them first. So we'll take the 0.526. We will subtract off the hypothesized value, 0.44, and we'll divide by that standard deviation estimate was 0.036. think I wrote these down before. I got like, let's see here, 2.39. All right, so this, I guess that's telling us what? That our data value, the p-hat from the data, is about 2.39 standard deviations above the mean. And immediately we know, oh, that's sort of on the unusual side, right? Down at the bottom, as a friendly reminder, interpret the z-score with the sentence. All right, here it is. Z was 2.39, and I guess we're saying this. We're saying our p-hat of what? Well, here percentages. 52.6% was 2.39 standard deviations above the hypothesized 44%. It's essentially what we've just discovered here. The data value was a good 2.39 standard deviations above that hypothesized 44%. More than 2 is unusual, more than 3 is rare. We're sort of squeezed in between. What we're going to do now is convert this to a probability. This is important. Rather than look at the standardized score, the 2.39, in hypothesis testing, we'll always next convert to a probability. It's called a p-value. And you'll be learning a lot about p-values over the final month or so of the course. And so here it comes. Let me flip the page. We'll just go right here. Top of the next bullet point. When running hypothesis tests, typically we'll base our decisions on a probability rather than a standardized value. We're at the standardized value now. We need to switch over. All right, so we'll clean this up. See what this says here. Determine the probability that we collected our sample. Here's what we got. Sent the students out to the parking lot. 52.6%. So determine the probability that we collected our sample, 52.6% large vehicles, or a sample even more extreme. It's important. I don't care exactly 52.6. Kind of like 52.6 or even further away. If our initial assumption was true, we assume 46% of vehicles were large. Read this until you understand it. I'm going to flip and do it, but this is sort of the whole logic of hypothesis testing for this example. So ask questions in class if you don't quite get it, because you need to. All right. On the next slide, you've got some space. You would use StatCrunch. And now you would use the normal tool on StatCrunch. As instructors, we're presuming you can do this now without us showing you on the video, so hopefully that assumption is true. Here's what I would do. Remember that the z-score was 2.39. Since we converted to z, we are using a normal model because p-hat is normal, and which normal model? It's the standard normal model. Remember, whenever I convert to z-scores, the mean is now 0, standard deviation is now 1. So when you're doing StatCrunch, it's the default, but just be cognizant that that's what you're using. Here's what the picture would look like. Nice normal model here. Even label it z for standard normal, centered at 0. The 0 corresponds to the 0.44, just to put it in perspective. That's the hypothesized value, but we standardize. Way up here is the z-score of 2.39. What does that correspond to? That corresponds to my data, which was p-hat 0.526. See how those values all fit together. What we're shading is whatever you're up here in the upper tail, you'll end up shading upwards. Using the normal model tool, you've got to be able to get that area at this point in the course. And so I'll just tell you that this area is, what is it? 0.0084. If you want to think of it as a percentage, this is 0.84%. And let's see, what the heck is it? This is the probability of getting p hat equal to 52.6% or bigger if the null is true. The null said, let's assume 44% of our students and faculty drive large vehicles. What's the chance, if that's true, that I draw this kind of sample or one even more unusual? Here's my sample. The shading is one even more unusual. What kind of probability is this? This is 0.084. This is very small probability, right? Think back to the z-score. It's a pretty unusual z-score. What is this? About 8.4 times? 8.4 times in, I guess, 1,000, right? 10,000, yeah. Pretty darn rare, less than 1 in 100, that we would get that kind of crazy sample, or one even crazier. All right, down at the bottom is the important stuff. When you run a hypothesis test, you got to pick sides. Either you're going to reject the null and move to the alternative, or you'll fail to reject and continue believing the null. So judgment call time. Let me clean this slide up. Can't be wishy-washy here. You have to pick sides and go with it. All right, let's see here. I guess there's two options. Option one, students. The null is true. The initial assumption that Cecil is correct. 44% of our drivers drive large vehicles, just like the ABC News story told us. Right? So that's true. And here's the big and. And something just happened which would only happen 0.84% of the time. Or about 8 in 1,000 times, or about 1 in 125 times. So read this one more time. The null is true. Exactly 44% of Cecil College drivers prefer large vehicles. And what just happened happened. And it's very rare that that would. You know, if you're a gambler and you've only got 8 in 1,000 odds, do you win often? Probably not, right? So that's option one. The tone of my voice kind of tells you that's not the right option, right? 2, because the data, here's option 2, because the data was collected, the data we collected has such a low probability of occurring, if the null is true. Then in all likelihood, the null is not true. It's a logic puzzle. Basically, you're saying, all right, either the null is true or not, and do I have data to support it or refute it? Because the data we collected has such a low probability of occurring, if the null is true, then in all likelihood it's not. Rather, that leads us to the alternative is true. The data have convinced us to change our minds. The p-hat of 52.6% driving large vehicles was compellingly higher than the 44%. We conclude at Cecil more than 44% of all drivers prefer. Right? Basically, here's option 2, and it's this last half a sentence. The data have convinced us to say this. We conclude at Cecil College more than 44% of drivers prefer those large vehicles. I go with option 2. The data convinced me to go with option 2. All right, so I guess it's judgment call time. And we're convinced enough. We feel pretty darn comfortable about that decision. Right? So there is one more page here to wrap up. And we're going to keep plugging on. Call it a day after that. Flip that page. Hang with me. I know it's a long video, but it's very important stuff. If I had to guess, as a student, you will probably do roughly 30 hypothesis testing problems from now to the end of the semester. So we've got to hammer this home. Important consideration number 1. We're not 100% convinced that more than 44% of Cecil College drivers prefer large vehicles. We concluded it, but we're not 100% convinced. In fact, with our decision, we're rejecting the no, we're going with the alternative. There is a chance we're wrong. Okay? And what's that chance? Because we rejected, I can actually put a number here to this one. There's actually that 0.84% chance that we made the wrong decision. It's less than 1 in 100. Can you live with that? Let's say you argued with your significant other and there was always only a 1% chance you were wrong. You'd feel pretty good about that, right? So 0.84% chance we made a mistake. If that's the case, the data have told us to do the wrong thing. I can live with this chance here, right? I can live with this chance of being wrong only 0.84% of the time. Second little part to this number one, big picture. This is a big picture video. When running hypothesis tests, we are using incomplete information about the population. How many cars could possibly come to Cecil College? Thousands, right? There's thousands of students, hundreds of workers. How many did we look at? 190. Because when running a hypothesis test, we're using incomplete information, namely the sample data. We'll always have a chance to make a mistake, students. Just hopefully the chances are small, right? Hopefully the chances are small. Chance of making a mistake with good data collection and an ample sample size should be quite small. All right, number two. We've concluded, right, at the end of this problem, we've concluded more than 44% of Cecil drivers prefer large vehicles. We still don't know exactly what the percentage is. Don't say now that, oh, it's 52.6%. Clearly. That's take another sample, right? You'd have to take a census of every vehicle to obtain that true proportion. Right? Be careful. Don't conclude at Cecil exactly 52.6% drive large vehicles. All we can really say is that it's more than 44%. Or can we say more? I know it's a long video, but here. Remember all that confidence interval stuff we did? We know that 52.6% is the best guess for Cecil College, but confidence intervals are very closely related to hypothesis tests. If we'd like to give a range of plausible values for the true proportion of all Cecil College students preferring large vehicles, we can support it with a confidence interval. Why isn't this on another video? But here we go. It's got to be 40 minutes this time. Real quick, because we're experts at confidence intervals. This p hat plus minus a z. Big square root p hat 1 minus p hat all over n. Most problems we do, it'll say run the test first. Support your answer with a confidence interval. Let's do it. The p hat value, this is the 0.526. We are doing what kind of confidence interval? Does it even say? Oh, say 95%. It doesn't say, but that's the most common one usually, so we'll do a 95% confidence interval. That'll tell me the z, and we'll just plug and chug. So, real quick, this would be 0.526 plus or minus 95% confidence interval is 1.96. Big square root 0.526, 1 minus 0.526. Pop it all over n, which was 190. Clean this up, add and subtract. You know what? Here's the final answer. I got a 45.4%. Converted to percentages as well. I got a 59.7%. What did we conclude at Cecil College? We concluded that more than 44% drive large vehicles. Check out the confidence interval. What do you notice about the confidence interval? The entire interval is above 44%. For the whole college, this is a range of plausible values with 95% confidence in terms of the proportion of all of us that drive large vehicles, right? So I'll just say that I won't write anything down. Feels like this video's been long enough. So, huge ideas. This is sort of the baseline for the rest of the semester, connecting this. And Kim Shepard will be back next time to give you the official steps, the official formulas, and talk a little bit more about p-values. All right, thanks for watching, and we'll see you in class.